All right, so let's continue here with section 3.6, do a couple more examples of implicit derivatives here. And as we saw from the last section, sometimes when we have a function that is not written in an explicit form, to find its derivative, we got to conduct what's known as implicit differentiation. All right, so recall, to find the implicit derivative of an implicit function, what we first got to do is take the derivative of our equation of our function from both sides with respect to the variable we're differentiating by, usually dx. Okay, so usually we take the derivative of both sides of our equation with respect to x, or whichever variable we're taking the derivative with respect to. And to find out the derivative of each side, we apply the rules that we have learned from chapter 2, so using the general derivative rules, except in this case, when we take the derivative of a certain term in our differential notation, for the numerator here, we have to denote the variable that we have taken the derivative of. So look at the example that we did. Our first term was a function of x. So here we say we take the derivative of a function of x with respect to x. The second term, that's a function of y. So we said in this case, we took the derivative of y with respect to x. And constants, as we have seen before, derivative of constants just zero out. So let's do a couple more examples here. Suppose we want to find the implicit derivative of dy over dx for this equation of y to the fourth minus x squared equals 2x. Okay, so again, following the rules, following the steps, the first thing we want to do here is take a derivative of both sides with respect to x, pretty much multiplying both sides of this equation by this differential here. So you're going to take d over dx and distribute that into y to the fourth minus x squared. And then on the side, do the same thing. Take this as the differential of d over dx and multiply by 2x. All right. So once again, treat this like a variable here. So we're gonna take this and distribute it to each term that we have in our equation. So we're going to take the derivative with respect to x of y to the fourth minus the derivative with respect to x of x squared equal to the derivative with respect to x of 2x. Okay, so now we take the derivatives of each of these terms like we usually would. So derivative of y to the fourth is 4y cubed. Right, bring the power down, decrease the power by 1. But now for our differential notation, however, again, we got to specify the variable that we took the derivative of in this notation. So in front of the 4y cubed, we're going to say that we took the derivative of y with respect to x. Okay, minus, what's the derivative of x squared? Derivative of x squared is just 2x. And once again, for our differential here, we got to specify in the numerator the variable that we took the derivative of. So here we took the derivative of an x variable with respect to itself. So we're going to have dx over dx equal to, well, once again, here we have another function of x, 2x. So here we're taking once again the derivative of an x variable with respect to itself. So dx over dx, and the derivative of 2x is just 2. Okay, now again, what we see here is when we take the derivative of a variable that is the same one that we're taking the derivative with respect to, these differentials here of dx over dx wind up canceling out. Okay, our differential cancels out when we take the derivative of a function of x that has that same variable. So continue on then. What we're left with now is we have dy over dx times 4y cubed minus 2x equal to 2. Okay, so now we got to use algebra here. And now what we're pretty much going to do is use algebra to solve for dy over dx to get this implicit differential. To get this implicit derivative here by itself. All right, so we're going to add 2x to the other side. It's going to have dy over dx times 4y cubed equals 2 plus 2x. Or let me rewrite that. Let me put the 2x first. 2x plus 2. And then divide. And now we have, it's again. So now we're left with this differential multiplying 4y cubed. But since this is what we're trying to solve for, let's now divide both sides by 4y cubed. All right, so I'm going to divide both sides by 4y cubed. Okay, leaving us with, so these two cancel out here. And now we're left with our implicit derivative of dy over dx equal to 2x plus 2 over 4y cubed. Okay, but not quite just finished here. Since we're dealing with a rational, since we have a fraction, recall for fractions, we want to try to simplify our solutions by cancel out any common factors between any separate terms. Look what we have here. Here we have a 2, 2, and a 4. What do these three terms have in common? A factor of 2. So we can take each of these three factors, we can take each of these three terms and divide by a factor of 3. So this 2 will become 1, this 2 will become 1, and this 4 will become 2. So our implicit derivative for this function of dy over dx is going to equal x plus 1 over 2y cubed. All right. Let's do 2 more here. Let's get some more practice with finding these implicit derivatives. Oops. All right, suppose for this next example, suppose once again we want to find dy over dx of the following function here. So our function will be, let's see which one. Let's do x squared times y cubed equals, say, 20. So x squared times y cubed equals 20. Okay, so again, following the steps, since our denominator is dx, that means we're going to be taking derivative with respect to x of each side. So we're going to take derivative with respect to x of x squared times y cubed equal to the derivative with respect to x of 20. All right, now be careful on this left-hand side here. Notice that the x squared and the y cubed are attached together. They're not being separated by subtraction or addition. They're attached together. They're multiplying one another. So if we want to find the derivative then with respect to x of the left-hand side here, then what we're going to have to do is apply the product rule. Whenever we have two functions being multiplied, if we want to find the derivative of their product, we got to use that product rule. Okay, so let's set up our two functions here. Let's call this f. F will be x squared, and then g will be y cubed. All right. So now we want to take derivative with respect to x of these two functions. Now this part we got to be really careful with. Since we deal with implicit derivative, to find f prime here, if we want to find f prime, that's going to be equivalent to take a derivative with respect to x of x squared. And if we want to find g prime, that's going to be equivalent, or that's going to equal to the derivative with respect to x of y cubed. Okay, for these two derivatives, we have to include also this differential of d over dx in order to find f prime and g prime. Okay, which will give us what here? All right, so here we get f prime, and since we're taking the derivative of x variable, that's going to be dx over dx. So dx over dx, oops, and the derivative of x squared is 2x. And then for the second equation for g prime, so take a derivative of y variable, then that's going to have this, then we're going to include that differential of dy over dx, and the derivative of y cubed is 3y squared. All right. So be careful on these implicit derivatives, especially when setting up the quotient or product rule. Once you define your two functions and then you go about finding the respective derivatives, we also got to include that initial differential of d over dx, because again, we're taking a derivative of this product here, of this entire product of these two functions with respect to x. Okay, so now we have f and g, we have f prime and g, we have f prime and g prime here. So now let's set up that product rule like we have done before. Okay, so I'll just rewrite this here. So again, here we have the derivative respect to x of x squared y cubed equal to the derivative respect to x of 20. And based on what we found setting up this product rule here, or setting up these four functions, then the derivative of the product of these two is going to equal, well, again, product rule, f prime. So take f prime, which was, oh, I forgot to do something here. Notice that for f prime, we have dx over dx. What happens to the dx over dx? Cancels out. So that cancels out, leaving us with f prime to just be 2x. All right. And from here on out, if we're taking the derivative of a variable that's the same as the denominator, we're just going to assume that it cancels out. Right? We're going to skip that step of showing that it cancels out there. Okay, so here we're going to have f prime, which is 2x, multiplied by g, which was y cubed, plus f, which was x squared, multiplied by g prime, where g prime was not just 3y squared, but dy over dx times 3y squared. So dy over dx times 3y squared equal to, what's the derivative of a constant? Just 0. All right. So now, we're going to do next, now that we have taken the derivative of both sides with respect to our denominator, time to use some algebra to solve for dy over dx. So what we can do here first is move all the terms that do not involve, that are not being multiplied by this differential to the other side, which in this case is 2xy cubed. Now these two are pieced together, are attached together through multiplication. So let's move that to the other side by subtracting it from both sides. So we're going to take 2 minus 2x y cubed from both sides of our equation. All right, so these two will cancel out. And now we'll be left with here, oops. Now we're left with this part here, where we have x squared times dy over dx times 3y squared. Let me move this differential in front of these two factors. All right, so we're going to have dy over dx times x squared times 3y squared. That's what we're left with on the left-hand side, equal to negative 2x y cubed. Well, we move from that side to the other. Okay, and then these two are attached together and multiplying dy over dx. Then to solve for dy over dx, here the next step, divide. Divide this entire piece of x squared, 3y squared, from both sides of the equation. Oops. All right, so these two cancel out, and we're left with that our implicit derivative of dy over dx is going to equal negative 2xy cubed over, and let me move that 3 in the bottom to the front, over 3x squared y squared. All right, but again, so let me just double check. All right, but again, we have a rational, we have a fraction. What we got to do with fractions, try to simplify them. Let's look at the coefficients first. Does 2 and 3 have anything in common? No. So these two have no least common factors. So in this case, 2 and 3 stay the same. But notice what we have here regarding the variables. We have one factor of x on top, two factors of x on the bottom. Here we have a common factor of 1x. So what can we do? Cancel out that common factor. So this 1x is going to go away, and this 2 on the bottom will become 1. All right. And now look at the y variables. We have 3 factors of y on top, 2 factors y on the bottom. So these two have a common have 2 common factors of y. So we can cancel out 2 factors of y from the numerator and denominator. So this will become 1, and this just goes away. Okay, leaving us with our implicit derivative of dy over dx equal to negative 2y over 3x. Okay. Again, for rationals, always try to simplify as much as you can. Try to cancel any common factor between the coefficients of each term, and then look at the variables and try to cancel out the least common factor or the greatest common factor of all your variables from every term. Okay, let's do one more example. One more example with 2 parts here. Okay, suppose we're given the following here. Given the following equation of, I'll just write it out, of y cubed minus y squared plus y minus 1 equals x. Given this equation for part A, let's find once again dy over dx. So dy over dx once again here. All right, so again, pretty much following the same steps here. So first step, take the derivative with respect to x of both sides of our equation. So we multiply each side by this differential of d over dx. So d over dx times y cubed minus y squared plus y minus 1 equal to the derivative with respect to x of, in this case, just x. Okay. Distribute differential to each separate term. So you're going to have the derivative with respect to x of y cubed minus derivative with respect to x of y squared plus derivative with respect to x of y minus derivative with respect to x of 1 equal to the derivative with respect to x of just x. Okay, and since here we just have individual terms, then this will be a straightforward derivative here. No need to use a product rule, quotient rule, no chain rules. In this case, let's use the power rule for each of these individual terms. All right, so the derivative of y cubed, that's going to be 3y squared. And since we took the derivative of y variable, then that's going to give us dy over dx as our differential here. Okay, minus, once again, another y variable. So minus the derivative of y with respect to x, the derivative of y squared is 2y. Plus another y variable, so another differential of dy, so plus dy over dx times derivative of y to the first power. Derivative of variable to the first power is just the coefficient, which in this case is just 1. Minus the derivative of constant, 0, equal to derivative of x with respect to x. We have an x term here, so our differential here will be dx over dx. And what's the derivative of x? Of just x? Only 1. All right. So now notice here on the left-hand side. On the left-hand side, we have 3 terms that include this differential of dy over dx. What we're trying to solve for, what we're trying to find. So what should we do here? Well, what do we do when we have a common factor between multiple terms? Pull out that common factor.
So let's take out the differential from each of these three terms here to give us dy over dx, and in parentheses, 3y squared minus 2y plus 1. All right, we don't have to worry about the 0 because 0 is just 0. Equal to, what happens on the right side? Well, since we have dx over dx, that differential cancels out, leaving us with 1. All right, and since we're trying to solve for dy over dx, so we want to get this by itself. Well, since this differential is multiplying this whole expression here, then to move this expression to the other side, we have to divide. So we're going to divide both sides by 3y squared minus 2y plus 1. All right, to give us, so these two will cancel out here. Oops. So these two expressions cancel out, leaving us with dy over dx by itself on the left-hand side, equal to 1 over 3y squared minus 2y plus 1. All right, and that's our solution for that implicit derivative of dy over dx. And nothing else we can do here because there's no common factors between these four terms. Okay. But suppose for part B. Suppose for part B, for the same equation that we have, suppose that instead of dy over dx, we want to find dx over dy. So kind of the inverse here. I don't say inverse, it's kind of reciprocal here. We want to dx over dy. And all the examples that we have done so far, our denominator was dx, but now our denominator for part B is dy. So we want to take rid of x with respect to y. Okay. So how do we go about this? So once again, we have that equation above of y cubed minus y squared plus y minus 1 equal to x. But now since we want to find the derivative of x with respect to y, since we want to find dx over dy, then in this case, we're going to start off by multiplying both sides of this equation by the differential of d over dy. So we'll take the derivative of each side of our equation with respect to y. Okay. Again, for these type of problems, the first step is to take the derivative of both sides of the equation with respect to what our denominator is. And since our denominator is now y, we're going to take the derivative with respect to y of each side of this equation. Okay, and the process after, and then the steps that follow, pretty similar. So once again, distribute the differential to each term. So on the left-hand side, we're going to take the derivative with respect to y of y cubed minus the derivative with respect to y of y squared plus the derivative with respect to y of y minus the derivative with respect to y of 1 equal to the derivative with respect to x of x. Okay. So let's see how our differentials here are going to change now that we're taking derivative with respect to y. So again, as I've mentioned, for these differentials, when we take derivative of a term, we have to include in the numerator that derivative, we have to include in the numerator here, the variable we are taking the derivative of. So what are we taking the derivative of in this first term? A variable of y. So our differential here for this first term will be dy over dy. We're taking the derivative of a function of y with respect to itself. And the derivative of 3y squared will be, the derivative of y cubed will be 3y squared. Minus, here we have another y term. So our differential will be dy over dy again. And the derivative of y squared is 2y plus one other y term. So once again, we're going to have another differential of dy over dy, and the derivative of y respect to y is 1. Minus derivative of constant, that still remains 0. Equal to, but now let's look at the right-hand side. Yep. Oops, that should be a y, not an x. But now let's look at the right-hand side. Here we're taking the derivative of a term of a variable of x with respect to y. So again, in the numerator, we have to specify the type of variable we're taking the derivative of, which in this case will be x. So we're going to have dx on top over dy. And what's the derivative of x? Just 1. Okay. Now, on the left-hand side, again, what do we have in each of these terms? A differential of dy over dy. What happens when we have the same thing on top as we do on the bottom? They cancel out. So this differential is gone, this one is gone, this one is gone, leaving us with 3y squared minus 2y plus 1 equal to, on the right-hand side, what do we have left? Dx over dy. Dx over dy. What are we trying to find? Dx over dy. So here we have that implicit derivative in x with respect to y. Okay, so here we see this equation. It's going to tell us how x is changing with respect to y. Now recall, dy over dx tells us the rate of change of a function, the rate of change of y with respect to x. Dx over dy would be the other way around. Dx over dy tells us the rate of change of x with respect to y. How x is going to change in the next instantaneous change, in y. Okay. So let me pause this second part of this section here, and we'll do one more part from 3.6 here when it comes to these implicit derivatives. Let's do that now.